everyone, stay safe ya. Today, we will share about line integral. This is the complex analysis and our lecturer is Dr. Kartono MSE. Let me introduce ourselves. We are from group 2. This is Nazzun. This is Innadien. And this is Alifah. So, we are students from Mathematics Department, Faculty of Mathematics and Natural Sciences, Universitas Negeri Semarang. So, we talk to the first material, complex functions from real variable. Suppose the derivative and integral of a complex function fz is real value w with a real variable t. A complex function of the real variable can be written as wt equals ut plus e vt, where u and v are real valued functions of variable t. The derivative of wt is as w prime t or dwt dt is defined as w prime t equals u prime t plus e v prime t. From this definition, we can define for each complex number constant z0 equals x0 plus y0. Then ddt for z0 wt equals ddt x0 plus y0 times u plus ev equals to ddt x0 u minus y0 v plus y0 u plus x0 v equals to ddt x0 u minus y0 v plus I ddt y0 u plus x0 v equals to x0 u prime minus y0 v prime plus e y0 u prime plus x0 v prime equals x0 plus y ey0 times u prime plus ev prime equals z0 w prime t. This is equivalence ddt exponential of z0t equals z0 exponential of z0t. Not all derivative rules on real functions in calculus apply to complex functions with real variables. For example, wt is continuous in the interval a less than equals t less than equals b, meaning u and v are both continuous in the interval. Even though w prime t is in the interval a less than t less than b, the average theorem doesn't apply anymore. In other words, it is not always true that there is a number c in the interval a less than t less than b. So, w prime c equals to wb minus wa over b minus a. To show it, assume that wt equals to exponential it for 0 less than equals to p. It is clear that w prime t equals to I exponential it not equals to 0. This means that the value of w prime t is never equal to 0. Whereas if we look for W prime t with the average theorem, we will get the result equal to 0 for 0 less than equals t less than equals to p. This is contrary to equation I. So, this is a definition. Certainly, integral for complex function of real variables wt equals to ut plus ivt a less than equals t less than equals b is defined as follows. The integral of wt dt from a to b equals to the integral of ut dt from a to b plus I integral vt dt from a to b, if each of the integrals u and v exists. Therefore, the real of integral wt dt from a to b equals to the integral of the real of wt dt from a to b, and the imaginary integral of wt dt from a to b equals to the integral of imaginary wt dt from a to b. This is an example. Example 1. This is a case that there are function of 1 plus it squared, and we must find the integral of this function where the interval is 0 till 1. So, the integral of function 1 plus it squared dt from 0 till 1 equals to the integral of 1 minus t squared plus 2it dt from 0 till 1 equals to the integral of 1 minus t squared dt from 0 to 1 plus I the integral of 2t dt from 0 till 1. This is the property of integral for the plus and minus this, and equals to 2 over 3 plus I. The existence of integrals u and v in the definition or equation 5 is guaranteed if the two functions of continuous fragments at interval a less than equals t less than equals b. For example, a continuous function everywhere in the interval except maybe at the limit point. Although not continuous, this function has unilateral limits. Of course, only the right limit is needed at a and only the left limit is needed at b. When both u and v are continuous piecemeal, then the function w is said to satisfy equation 5. The nature of the operation of the integral of the real functions below also applies to the integral function of a real variable. The integral of wt dt from a to b equals to the integral of wt dt from a to c plus I times integral of wt dt from c to b. It is just separate the AB and the middle interval is C. So the interval is separated into A till C and C till B. Let function Wt equals to ut plus I Vt and Wt equals to ut plus I Vt continue at interval A less than equals t less than equals b. If w prime t equals to w small t at interval a less than equals t less than equals b, then pq prime t equals to small ut, and big v prime t equals to small vt. So, by the definition, the integral of wt dt from a till b equals to ut, and we substitute the value of b and a plus ivt with the substitute value of b and a equals to ub plus ivb minus ua plus iva. Therefore, the integral of wt dt from a to b equals big wt with the substitution value of b and a equals to wb minus wa. We go to the example 2. Given d exponential it dt equals to I exponential it, so calculate the integral of exponential it dt from 0 till p over 4. So the solution is the integral of exponential it dt from 0 till p over 4 equals to negative I exponential I p over 4 plus I equals to negative I plus negative I times by 1 over square root of 2 and I over square root of 2 plus I equals to 1 over square root of 2 plus I times 1 minus 1 over square root of 2. To determine the nature of the absolute value of an integral, assume that a less than b, and the value of the integral defined in equation 5 is a complex number that is not equal to 0. If r0 is a modulus and theta 0 is the argument of the constant, then the integral of w dt from a to b equals to r0 times exponential negative I theta 0 equivalent to r0 equals to the integral of exponential negative I theta 0 times w dt from a to b. The left and right sides of equation 1 are real numbers. The real part of a real number is the number itself. Based on the definition, the real of integral w t dt from a to b equals to integral real w t dt from a to b, and the imaginary integral w t dt from a to b equals to integral of imaginary w t dt from a to b. Then the right side of equation 1 can be written integral of exponential negative I theta 0 w dt from AB equals to real integral of exponential negative I theta 0 w dt from A to B equals to integral of real exponential negative I theta 0 w dt from A to B. Thus, the equation 1 becomes r0 equals to integral of real times exponential negative I theta 0 w dt from A to B. The real of exponential negative I theta 0 w equals less than equals the mutlak value, the absolute value I mean, exponential of negative I theta 0 w equals to the absolute value of exponential negative I theta 0 times the absolute value of W, so equals to the absolute value of W. Based on equation 2, then R0 less than the integral of absolute value of W dt from A to B, so that the absolute value of integral Wt dt from AB less than equals integral of absolute value Wt dt from A to B for A less than B. So, the last conclusion is the absolute value of integral Wt dt from A to infinite less than equals the integral of the the absolute value of Wt dt from A to infinity. Thank you.
Now we are going to learn about contours, but before that we have to learn about curve. If g and h are real continuous functions of the real variable t in the closed interval ab, then the set of points gt, ht in the xy plane will form a curve. So, a set of points z equals x plus iy in complex plane is a curve if x equals gt and y equals ht, with g and h as a continuous real function of variable t and t element of interval ab. Points ga plus iha is called the initial point, and point gb plus IHB is called the endpoint. If there is no point on the curve that corresponds to two different t values in interval AB, then the curve is called a single curve. A curve whose starting and ending points coincide is called a closed curve, and closed curves that don't cut themselves are called single closed curves. Curves that are not closed are called open curves. If we have a curve C as a set of z equals gt plus iht, where a less than or equals t and t less than or equals b, with g prime and h prime are continuous on interval ab and not simultaneously 0 for t element of interval ab, then C is called smooth curve. The terms g prime and h prime guarantee that the tangent gradient in point gt ht at C changes continuously when the variable moves from a to b in interval ab, and this is the reason why the term smooth is used. And now we are going to learn about contours. A contour is a directed curve which is made up of a finite sequence of directed smooth curves whose endpoints are matched to give a single direction. This requires that the sequence of curves C1 until Cn be such that the terminal point of Ci coincides with the initial point of Ci plus 1 for all I 1 less than or equals I less than n. I mean, this is not counter but contour. A contour C can be written as C1 plus C2 plus on until plus Cn. There are many kinds of contour. The first is single open contour. Single open contour is the contour where the starting point here and the end point here doesn't coincide and doesn't cut itself. Doesn't cut itself means that the contour is a single contour. And for the next, multiple open contour. The contour where the starting point here and the end point here doesn't coincide and cut itself. We can see that there are many intersection points such as this and many other. So this contour is called multiple open contour. And the next is multiple closed contour. The contour where the starting point here and also the endpoint are coincide. You can see at this figure and cut itself. So this counter is called multiple closed counter. And the next kinds of counter is single closed counter. A counter where the starting point and the endpoint coincide and doesn't cut itself is called single closed counter. And suppose C, a single counter with equation x equals gt and y equals ht, and a less than or equals t and t less than or equals b. Positive direction C determined as the direction of the counter from initial point to the end point. If C is a single closed counter, then if we move forward to trace C such that it reaches the interior area or interior C is on our left. So we call this positive direction, while the opposite direction is called the negative direction. And this figure is the example of single closed counter with positive direction. We can see that if we move forward to this counter, we can see that the interior point is on our left. And then for single closed counter with negative direction, you can see at this figure. If we move forward to trace C, so we can see that the interior of C is on our right.
Jordan curve theorem. Definition: if a single closed path is on a plane, then the plane is flat, will be divided into three mutually exclusive parts as follows. First, the curve itself. The second, interior, which is an open and limited set. The third is exterior, which is an open and not limited set. Here is the curve of the Jordan curve theorem. The curve is the boundary of the interior set and the exterior set. Example: defined lines z equals to x plus ix if 0 less than equals to x less than equals to 1, or x plus I if 1 less than equals to x less than equals to 2, consisting of line segments from 0 to 1 plus I followed from 1 plus I to 2 plus I is a simple trajectory. Suppose a derivative g prime t and h prime t is a derivative of components function that describe the path C, there is, and is continuous along the interval a less than equals to t less than equals to b, then C is called the differential path. Derivative of C prime t is C prime t equals to x prime t plus I y prime t. A real valued function, the absolute value of C prime t equals to the square root of the is the square root of x prime t squared plus y prime t squared, is a function that can be integrated throughout the interval a less than equals to t less than equals to b. Length of the track L equals to integral from a to b the absolute value of c prime t dt. Suppose t equals to p tau, that where p is a real valued function that maps interval a less than equals to tau less than equals to beta, then the length of track C form this inequality, or it can be written by L equals to integral from alpha to beta the absolute value of large C prime tau d tau, with C prime tau is equals to the absolute value of C prime p tau times p prime tau. Upper limit modulus of integral contour. C is defined as a contour C equals to Ct times A less than equals to T less than equals to B. The absolute value of integral contour Fc dc is equals to the integral of from A to B, where Fc times C prime T dt less than integral of A to B, the absolute value of Fc times the absolute value of C prime T dt. For the non-negative constant m, the absolute value of Sc less than equals to m. That is, the absolute value of integral contour Fc dc less than equals to ml. Note that because all integral trajectories are contours and integrals are continuous functions defined in contours m that appear in equality, the absolute value of the integral contour Fc dc will always be there. This is because the real valued function Fc is continuous at closed bounded interval a less than equals to t less than equals to b if f is continuous at c, and the function always reach a maximum value of m at that interval. Then Fc has a maximum value at c when f is continuous, so f is continuous at c. That's all our presentation. Thank you.